In this lecture, we will look at magnetic fields produced by currents. So far, we've learned that current-carrying wires can experience a force when placed in a magnetic field, and specifically when the direction of the current and the magnetic field are not parallel or anti-parallel. So we had this equation for the magnitude of the magnetic force. So magnetic force is the current times the length of the current times the magnetic field times sine of the angle between the magnetic field and the direction of the current. Now the direction for the magnetic force was given by the right-hand rule. Then in 1820, a Danish physicist by the name of Hans Christian Ørsted noticed that a compass needle deflected in the presence of a current-carrying wire. So he drew the conclusion that currents also produce magnetic fields. So his big contribution to physics was noticing that current-carrying wires create magnetic fields around them. Also in 1820, I guess it was a busy year, Jean-Baptiste Biot and Félix Savart developed an equation for calculating the magnetic field produced by current-carrying wires. We're not going to discuss this Biot-Savart law, but we will look at some specific examples for magnetic fields produced by specific types of wires. So first we'll start with a long current-carrying wire, and by Biot-Savart law, we ended up with a magnetic field. The magnitude of the magnetic field of a current-carrying wire is mu naught I over 2 pi r, where mu naught is called the permeability of free space, and it's equal to 4 pi times 10 to the negative 7 Tesla meters per amps. Now the direction of this magnetic field is given by a right-hand rule. It's not one that we have seen before, so let's look at it. Let's say that we have a current-carrying wire, and that's this thin wire over here. The direction of the current is up, and let's look at this little video and see how we figure out the direction of the magnetic field due to this current-carrying wire. So we have the direction of the current up. We place our right thumb in the direction of the current and then wrap our hand around the wire, and the magnetic field will be around the wire in the direction of our fingers. So the magnetic field would be rotating about the wire in the direction of our fingers. So let me draw an arrow here for the magnetic field. So it goes this way, but it's basically rotating around this wire. So that means that on the right side of the wire, the magnetic field would be into the page, and on the left side of the wire, the magnetic field would be out of the page in the direction of the fingers. So this would be the magnetic field. So here we have another drawing of it. The wire has a current going straight up, and we wrap our hand around the wire, keeping our thumb in the direction of the wire, and the direction of our fingers is the direction of the magnetic field. Now another shape of wire is a loop, and the magnetic field has a magnitude of n, which is the number of turns in the loop, times mu naught I. Mu naught again is permeability of free space, I is the current in the wire, in the loop, divided by 2 times r, where r is the radius of the loop. The direction is also given by that right-hand rule. So let's look at this. Here we have a drawn loop of wire, so there are several turns to this wire, and there is a current going in that direction. And here I made a little loop of wire out of actual wire. So let's look at the video and see how we do the right-hand rule. So we notice the direction of the current in that drawing, so we match that up to the direction of the current in the little red loop here. And then we place our thumb in the direction of the current, stick our hand inside the loop, and the direction in which our fingers point out of the loop is the direction of the magnetic field. So again, the thumb goes in the direction of the current, so the thumb goes in around that way. We place our fingers, we place our hand inside the loop, and the direction of the magnetic field will be in the direction of the fingers. So that is magnetic field B. So in the loop here, magnetic field would be in this direction. So here we have a drawing again. So in this situation, we have the current going around in this direction. The thumb is parallel to the current. The fingers are inside the loop, and they're sticking out of the loop. So the magnetic field then is going to be up. Another shape of a conducting wire can be a solenoid. So it looks kind of like a slinky. The magnetic field, its magnitude due to the solenoid is mu naught times lowercase ni. Mu naught is permeability of free space. I is the current in the solenoid. N is the number of turns divided by the length of the solenoid. Not the length of the wire, but the length of the solenoid. The direction of the magnetic field is given by the right-hand rule. And here we have another little video. So this is my solenoid. So I have a current coming from back here. It's going to circle around like that. So in the front, it's going to the right. Behind the solenoid is going to the left. So that's the direction of the current. And here I manufactured solenoid out of wire, and I wrapped it around the glass. So let's see how exactly we do the right-hand rule for this. So we follow the direction of the current. So we notice that the current goes around like that, meaning that for the glass, the current goes around in this direction. So we place our thumb along the direction of the current and then place our hand inside the solenoid. The direction of the magnetic field is the direction of the fingers inside the solenoid. So here, since my fingers are in that way, this is also the direction of the magnetic field. So on the drawing here, the magnetic field goes in this direction. So here is a drawing again. We have a current in a solenoid, so the current goes around this way. We place our thumb along the direction of the current. We stick our hand inside the solenoid. So the direction in which our fingers are inside the solenoid is the direction of the magnetic field. So in this case, magnetic field goes to the left. And I mentioned the fact that the length is the length of the solenoid. So if I just draw a line here, this would be the length L that corresponds to this length over here. And the number of turns, well, in my solenoid here, I have 1, 2, 3, 4, 5, 6 turns of wire. So lowercase n then would be the 6 turns of wire divided by this length L. So here we've seen how different configurations of current-carrying wires produce magnetic fields of these different magnitudes, and how we apply the right-hand rule. Again, we have to place our thumb in the direction of the current and then curl our fingers and get the magnetic field that way. I would like to thank my son for filming my little videos and my husband for getting rid of the background noise in those videos. I was filming outside, so they helped me in making this lecture.